All right, hello everyone, and today's video will be on number systems, specifically base 10, which is what we normally work with, binary, octal, and hexadecimal, as well as an introduction to Boolean algebra, which is how we're able to mathematically manipulate these numbers to get desirable results. So without further ado, let's go ahead and hop into it. So first, we're going to start with an overview of base 10, which is what most students are comfortable working with, because this is what we work with in our daily lives. Okay, so first we'll take the number 123, for example, or 123, and we'll assign place values to all of these digits. So you can see the 3 is in what we call the 0th place, the 2 is in the first place, the 1 is in the second place. So we're able to use the actual digit in the place as well as the place itself to create this expansion. So if we look at it, the red numbers, 2, 1, and 0, all line up with these bottom three places. So we start with taking the 1 and multiplying it by 10 to the 2, since it's in the second place. And then we follow this pattern, multiplying 2 times 10 to the 1, since it's in the first place. And then finally, 3 times 10 to the 0, since it's in the 0th place. All right, so this is kind of the same framework we're going to use when expanding from binary, from octal, from hexadecimal into our base 10. So let's go ahead and do an example of binary or base 2. So here we have 1101 and there's 4 bits, so places 3 to 0. So since it's base 2, there's 2 options, 1 and 0, just how in base 10 there's 10 options, 0 to 9. So as we do this expansion, it's identical to base 10. You take the physical digit in the place, which is 1, and then multiply it by our base, which is 2, to the power of the place it's in. So we go ahead and expand this out and continue to convert. 1 times 2 to the 3. 2 to the 3 is 8 in base 10, or what we consider normal, plus 4. Anything multiplied by 0 is going to be 0, and 2 to the 0 is going to be 1. So this would be plus 0, and this would be plus 1. So if we do this addition, we should find that it equals 13. So now we'll move on to hexadecimal, and we'll take the same number, 123, but now there's a subscript of 16 indicating that our radix, or our base, is 16. So we'll continue this process. 1 times 16 to the 2, 2 times 16 to the 1, 3 times 16 to the 0. So expanding that out, 16 squared is 256. 2 times 16 is 32. And then 16 to the 0 is 1 times 3 is 3. And we'll see all of this adds up to 291 in base 10. So the same process can be used with whatever base. Whether you're working with base 8, you'll have, I don't know, some digit 2, like times 2 to the, or I'm sorry, times 8 to whatever place you're in. Same thing for less common bases like base 37. So apply this framework and you'll be able to go from whatever base back into base 10. This is easy for when you need to check your work. All right, so now we're going to start with conversions. So let's say we have this number 357. This is in base 10. Binary coded decimal is a legacy way we used to express these base 10 numbers in ones and zeros. And it's the easiest to understand, but it's not as efficient when you have a limited range of bits. So what you do is you take the 3, and in 4 digits, you express this 3. So 0011 is 3. Then you move on to 5 in 4 digits. This is 5. Following the sequence, this is 7. So 357 is expressed in this way, but notice it takes 12 bits. So that's not great. So in modern times, we've kind of moved away from this, but it's important to know and know how to convert. So now if we have binary, so if we have this base 10 number, 357, and we want it to convert it to binary, Um, you take the number, so 357, and actually, let me fix a quick error. So this would actually be 357 base 10, and then this, instead of base 2, this would be BCD, right? So this indicates what base it's in. Yeah, sorry about that error. Okay, so moving back into converting from base 10 into binary, you take the base 10 number, in this case 357, and divide it by 2. So 357 divided by 2 will be 178 with a remainder of 1. So now you take this result in the second column and put it into the division column, and you'll multiply this by 2. So 178, you can see 8 is kind of an even number. So you'll get 89 with a remainder of 0. And you basically continue this process all the way down, and we'll skip to 2 divided by 2. We know that's 1 with 0 remainder. We'll take this 1 into the division column. And now we have 1 divided by 2, which is, you can't express in an integer. So it's essentially 0 with a remainder of 1. And once you have this result as 0, you know you can stop. And now if you look in this remainder column, you can see we only have zeros and ones, which makes a lot of sense if we want to convert to binary. So now you take this column, and this last one right here will be MSB, or most significant bit. And you'll take this one right here, and it'll be our least significant bit. So if you go ahead and write this out, with this one being the one right here, and this one being the one right here, you get a binary representation of 357. So if you want to do it on your own time, is convert this number back to 357 using the skills we learned previously. Feel free to do that. So now let's move into hexadecimal. So the good thing about binary is it's kind of our bread of butter in terms of converting. So once you have a number in binary, it's very easy to go into hexadecimal and then octal as well. So for hexadecimal, we take this binary number and we'll rewrite it. And you want to group this number into groups of 4, which is easy because typically when you write out long strings of binary, you naturally group them by 4. So in this PowerPoint, I added colors so it's easier to differentiate. So you take this grouping of 4 and then you directly convert it to base 10. So 0, 1, 0, 1 is 5. 0, 1, 1, 0 is 6. The 1 goes directly into this. So if we look at the blue 0, 1, 1, 0, that's basically like saying 2 to the 2 plus 2 to the 1. So that's 4 plus 2 equals 6. So that's how we get the 6. And then if we have octal, it's very similar, but instead of groups of 4, that's 101 becomes our 5, and 100 becomes our 4, and then 101 becomes our 5 again. So usually going in and out of the division, we have binary, hexadecimal, and octal. So now that we've done some conversions, let's talk about how we can do these operations. So when you first start doing addition in kindergarten, it might not seem very intuitive, but now that you do it every day, it's like a second thought. The same can be said for binary here. So if we start with this first, we have 0, 1, 0, 1, which I have pre-written equals 5. And we have 1, 0, 1, 1, which I've pre-written to say that equals 11. So we'll use these numbers in blue to check our work. So just like we were doing normal addition, 1 plus 1 is, so 1 plus 1 is actually 1, 0 in binary. So of course 1, 0 is equivalent to like decimal 2. So we'll write 0 and we'll carry our 1. And now we have 1, this one right here, plus 0 plus 1, which again is 1, 0. So we'll do 0 and we'll carry our 1. And then same thing, 0, carry our 1. And then we'll do 0 and we want to carry our 1, but you can see there's no number we can carry it to. So off to the side here, I'll put in parentheses our 1, which is what we're going to call our overflow, which means we actually can express this new number in 4 bits. Because if it makes sense, if you have a 4-bit number, 4 bits, and they're all 1, so 1, 1, 1, 1, if you convert this back to base 10, it's actually 15 base 10. And we know 5 plus 11 is 16. So the max we can represent in 4 bits is 15, which is why you have this overflow when you try to calculate the value of 16. Okay? So now let's go ahead and move on to subtraction. So subtraction follows the exact same thing as it would in base 10. 0 minus 0 is going to be 0. 1 minus 1 is 0. And now you have 0 minus 1. So just like in base 10, we're going to take this 1, we're going to borrow it. Now it's going to be a 0, and this 0 becomes like a 1, 0, or you can kind of think of it as a 2. So now you have 2 minus 1, which is 1, and then 0 minus 0, which is 0. And now we can check our work, 10 minus 6, and this number is indeed 4. And then same thing with multiplication. So 1 times 0 is 0, 1 times 1 is 1, 1 times 1 is 1, 1 times 0 is 0. So I'll go ahead and then, of course, when you move on to the next digit, you add this placeholder 0 and you continue to work. So 0, 1, 1, 0. And then, of course, since these last two are 0, these all will be 0. And then we'll add this up. 0, 1 plus 0 is 1, 1 plus 1 is 0, carry the 1, 0, carry the 1, 1. So you can see we kind of run into this same issue where our answer is 18, but remember we can only express up to 15 in 4 digits. So if we want to write 18, we need to actually use 5 bits. So if you work through the math, this 10010 does convert back to 18. Okay, so now we're going to do division, which I've left a lot of room for because sometimes it gets a little long. So we'll do long division here. So we'll have 100 on the outside, and then on the inside we'll have 1, 1, 0, 1, 0. I'll put it inside. So 1, 0, 0 can go into 1, 1, 0 one time, and you multiply this 1 by whatever on the outside, so 100 or 100, and we'll subtract 0, 1, 0, and 100 can't go into 0, 1, 0, so we'll pull down this 1. 100 can go into 101 one time. It'll be 100 again. This will give us a value of 1. Of course, 100 can't go into 1, so we'll pull down this 0. And we find that 100, or I'll say 100, for the sake of clarity, can't go into 10 or 10. So it can actually go 0 times, and 0 times 100 is 0. Let's see, 10, and now we're out of places. So we'll do just like how we would do in long division. We can say that our answer will take whatever on the top, 110, this is in base 2, with a remainder of 10 base 2. So yep, that's what we got. Or equivalently, if you want to go into decimal, you can add a decimal here, you'll add a 0, and then you'll be able to pull this 0 down to come help. And you can see this goes into this perfectly one time. So we'll add the decimal here and add a 1. And then we'll subtract. You can see now we even it out. So this would be another correct representation of this operation using a decimal. So we can check our work by, of course, converting this back to base 10, but for the sake of time, I'll let you guys do that on your own. So lastly, we're going to talk about signed numbers, which I find is the most confusing for a lot of students. So I'm going to start with sign magnitude because I believe this is the easiest to interpret. So in terms of sign magnitude, the question is how can you represent a negative number in binary with ones and zeros? Well, as you learn in class, there's a lot of different ways, whether that be sign magnitude, one's complement, or two's complement. And you can have the same raw binary data, but since you're the designer, you can choose how to interpret this designer. So one person might have a set of 4 bits that they're interpreting using sign magnitude, and another designer might have the same 4 bits, but it'll be a different base 10 number because they're interpreting in a different way. So yeah, of course, these are the 3 main ways you'll run into. So sign magnitude, the most significant bit, MSB, indicates if it's negative or positive. So if it's negative, then you'll have a 1 in the MSB. And if it's positive, you have a 0 in the MSB. And for the ones complement, if you're given like raw binary data, what you do is you flip all of the zeros to ones and you flip all the ones to zeros. Okay, and then for two's complement, you basically take the ones complement, which is zeros to ones to zero, and then you just add 1 to the end. So here is an example of a decimal number converted to all of these signs. So you can see if you just look at the first or the last 3 bits, this is 4, and then the most significant bit is 0 to indicate it's positive. But if we want to express a -4, we keep the same 100 format and we just make the most significant bit 1. And this pattern repeats itself for 6 and -6, and then 9. And one thing to note is you won't be able to express -9 in sign magnitude because you need this extra bit. So we'll get into that at the end once we do the rest of these. So of course, one's complement, you have 4 to 0, 1, 0, 0. And you can see we flipped all the bits here for the ones complement. And then kind of the same thing for this. So I'll let you guys kind of look at this on your own. And then going from one's complement to two's complement, all we do is add 1. So here you have 2 ones get fed into this 0, and they become 0. It's more evident with this one. But yeah, you can kind of see the pattern here. So all of these are mostly 4 bits, and they represent different ways of representing the same number, is the idea. So the reason I crossed this out was because to represent, let's say 9 in one's complement, you need this 5th bit. So this 5th bit is necessary, but if you only have 4 bits, then it wouldn't be possible. So that's something to consider as you design and as you interpret some of these numbers. Yeah, so that is going to be the end of the video today. Thank you for watching.